This lesson deals with Supplemental Problem 2.5. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems at page 9. Let's look at an actual diode. The 1N4001 is a diode that we use in the 303 lab. And what I'm going to do is grab the data sheet for this. The reference at the bottom of the page refers to a Motorola semiconductor data library. This is a kind of a thick book. It had quite a few volumes. I'm taking this out of volume 1, what's called the discrete products of series A, and taking a look at page 1-86. Let me pull this up here, and this is actually the page before it. The data sheet has a lot of information on it. First of all, the number itself, and then some of its ratings. I'll talk more about this a little bit later in the course. And then electrical characteristics and then mechanical characteristics and some physical description of the device. This is page 1-85. And on page 1-86, there's a plot of the current through the diode versus the voltage across it. But you can see here it looks kind of bizarre because this is a log scale. So when we're looking at an exponential, it'll be a straight line. Eventually we'll talk about this over here, which is actually the resistance of the contacts of the wires going into the semiconductor. I grabbed two data points off of here. One at 0.8 volts, which was about 0.1 amp, which is 100 milliamps. And then the other point over here on the bottom at 0.6 volts, and the value about 1 milliamp. That's where this data is coming from. What I like to do is figure out the value of eta and I sub s given two data points. Because I have two unknowns, I would need two data points. Let's take a look at how we're going to solve that. In the Chapter 2 notes on page 13, we had a formula for calculating the change in voltage based on a change in current. And this formula didn't depend on the value of I sub s. See if we can use this formula to solve for eta and then eventually I sub s. Let's just take this equation and solve for eta. Eta is going to be equal to this difference divided by v sub t and divided by the natural log of the ratio of the currents at two different data points. This is 0.8 and 0.6. The difference is 0.2. This data was taken at room temperature, and so v sub t is about 26 millivolts. And then we have 100 milliamps at the second data point and 1 milliamp at the first data point, and that gives me 1.67. Now, for each of these data points, I have the Shockley equation, and we're strongly forward biased, so we could throw away the 1. I could use either the first or the second. It's going to be equal to I sub s times e to the v sub d, in this case data point 1, divided by eta v sub t. And I can solve for I sub s. Divide through by this term, so I get id1, and then the reciprocal of something raised to a power is just a negative of it. I'm going to use that data point of 1 milliamp and 0.6 volts. Found eta to be 1.67. And again, we use 26 millivolts here. And I get almost a nanoamp. It's actually 997 picoamps. And so these are my values for the Shockley equation that I can get from datasheet data. In ECE303, we'll actually have a lab, number 3, where we collect the data and then find the value of eta and I sub s. And lastly, here's where I grabbed that data sheet from. A reference that you could find by just searching the web for this and be able to find the same data points that I found. And this is Supplemental Problem 2.5.